For almost 1 million years, our planet's atmosphere had a pretty steady rhythm. A natural back and forth. But lately, something's different. Something broke that rhythm. So today, we're going to crack the code on this unnatural spike and figure out exactly what's going on.
So this is the big mystery, right? We have data going back hundreds of thousands of years that shows CO2 levels going up and down, like clockwork. But then all of a sudden, the pattern just breaks. It goes haywire. So the big question is, what happened? What was the trigger?
And when you zoom in on just the last few hundred years, wow, it is staggering. What used to be a gentle wave suddenly becomes a nearly vertical wall. I mean, look at that. This is the sharpest rise we've seen in 800,000 years. To figure out why, we need to put on our detective hats.
Okay, so every good investigation starts with a timeline, right? We need to figure out exactly when this crazy shift started to happen. That's going to be our first real clue.
The data points us to two key moments. It looks like the slow creep upwards started way back in the mid-1800s. But the huge acceleration, that's the part that looks like a hockey stick, that really kicks into high gear around 1950. So these two dates, they're major clues for our investigation.
All right, now that we have our when, we need to ask the next logical question. What in the world was going on around the mid-1800s and then again around 1950? What was happening that might be connected to all this?
And this is where it gets really interesting. This period was a time of massive, massive change. We're talking about the Industrial Revolution. First, you have steam engines showing up, all powered by coal. Then in the 1800s, coal use just explodes. And get this, right around the time our CO2 levels start to climb, we figure out how to drill for oil. A few decades later, we're putting that oil, refined into gasoline, into the very first cars. It was a complete energy revolution. Humanity was unlocking these powerful new ways to run, well, everything.
And these new sources of energy, the coal, the oil, the natural gas, we call them fossil fuels. They're basically these huge underground stashes of energy. Think of it like super concentrated, ancient sunlight that was captured by plants and animals millions of years ago, buried and cooked under pressure. And we figured out how to dig it all up and burn it to power our world.
So, we've got a prime suspect, our newfound love for using fossil fuels. But a good detective needs more evidence than that. Let's see if we can find a pattern by looking at a few other key trends from the same time period.
And boom, there it is. The pattern is just impossible to miss. When you put world population, fossil fuel use, and atmospheric CO2 on a chart together, they tell the exact same story. Each one is pretty flat for a long, long time, and then they all shoot straight up in a massive spike. The lines are practically tracing each other.
And this isn't just a story about more people being born. That's a huge part of it, for sure. But it's also about consumption. As our societies grew, each person started using way more energy to power their homes, drive their cars, and buy stuff made in factories. So you have more people, and each person is using more energy. That combo just led to a massive, massive increase in the total amount of fuel being burned.
And this brings us to the most important question you can ask in an investigation like this. Okay, we have a really strong correlation. 3 things all skyrocketing together. But is it just a coincidence? Or is the rise in people and fuel use actually causing the rise in CO2? To prove that, we need a smoking gun.
So to prove that one thing causes another, we got to go beyond the charts and dig into the basic science. We need to find the direct, physical link between burning a fossil fuel and creating CO2 gas.
And lucky for us, we can do that with a really simple test. Just imagine we take a fossil fuel, say the butane, in a lighter, and we put it in a sealed box with an air sensor. We get a baseline reading of the air inside. Then we ignite the fuel, let it burn out, and then we measure the air again. Simple, right?
And the results? They're totally conclusive. After the butane burns, the sensors show a big spike in 2 specific things, carbon dioxide and water vapor. So the fuel didn't just disappear, it was chemically changed into something else.
See, this isn't magic. It's just chemistry. The process of burning, which scientists call combustion, is a super predictable chemical reaction. When you take a fossil fuel and add oxygen and a spark, you get a reaction that releases a ton of energy. But it also creates byproducts. And what are those byproducts? Carbon dioxide and water. This right here, this is our smoking gun, the direct proven link.
So now we can put all the pieces of the puzzle together.
We can actually trace the whole journey of this carbon, from being locked away deep in the ground to floating around in our atmosphere.
So what's actually in a fossil fuel anyway? Well, if you could zoom in on a molecular level, you'd see they're mostly made of long chains of two types of atoms, carbon and hydrogen. That's why they're called hydrocarbons. And that C for carbon, well, that's the key ingredient we've been tracking this whole time.
And this quote just sums it all up perfectly. We're literally taking carbon that was buried and stored underground for millions of years. It was locked up, out of the way. We dig it up, we burn it for energy, and in that process, we release all that ancient carbon directly into the atmosphere as carbon dioxide.
So the picture is now crystal clear. You have a growing world population that is consuming more and more energy per person. That energy comes from burning fossil fuels. And we now know that when you burn fossil fuels, you get CO2 as a byproduct. It's a direct chain of events. The mystery of the spike? It's solved.
So we did it. We cracked the code. We followed the carbon from the ground all the way up into the air. But solving one mystery just opens up another one, doesn't it? We know what's causing the spike, but the brand new question is, now that all this extra CO2 is in the air, what happens next?